In this video, we're going to discuss multiple regression analysis. But let's start off with a review. We talked about correlation before, and what does correlation provide us? Correlation provides us the strength and direction of a relationship between two variables. With correlation and simple linear regression both, we focused on the relationship between two interval or ratio level variables. We looked at the strength of the relationship, measured as a correlation coefficient, and that can range from -1 to +1. The closer to the -1 or the +1, the stronger the linear relationship. The closer to 0, the less likely you are to have a correlation or a relationship between the two variables, and at 0 there is no correlation or relationship between the two variables. What does simple linear regression provide us that correlation doesn't? The linear regression equation expresses the linear relationship between the two variables and the ability to predict based on the relationship. The regression line describes the overall pattern of a dependent or outcome variable to a single independent explanatory or predictor variable. With multiple linear regression, we add additional independent variables, and they're denoted as x sub 1, x sub 2, etc., to better predict or explain the dependent variable y. So let's jump right in. Here are our objectives. Simple linear regression is a model we use to predict the value of one variable from another. With multiple regression, it's a natural extension of the simple linear regression model, and what we do is we use it to predict the value of an outcome from several predictor variables. It's a hypothetical model of the relationship among several variables. We've provided a link here to a UCLA website that provides instructions for performing different statistical analyses using SPSS and a few other statistical programs. It's a great website to use. So when do we use multiple regression? Well, we use it when we have one or more interval independent variables and or one or more categorical independent variables. We can take a look at the equation for multiple regression. It should look very familiar to you. The top equation is the general multiple regression equation with n independent variables. And the bottom equation is what we use when we're estimating our regression model. In this example, n is the number of independent variables that we have. X sub 1 all the way out to x sub n are the independent variables. B sub 0 is the y-intercept, in other words, the value of y when all of the independent variables are 0. It's the point at which the regression plane crosses the y-axis, the vertical. And B sub 1 is the net change in y for each unit change in x sub 1, holding x sub 2 to x sub n constant. It is called a partial regression coefficient or just a regression coefficient. When we did simple linear regression, we called it B1, the slope of the regression line. You'll see the subscripts written as numbers or some kind of abbreviated label for the variable name. For example, you might see B sub age instead of B sub 1. As we did with simple linear regression, we use the least squares method to develop the equation. Determining B sub 1, B sub 2, etc., all the way out to B sub n manually is very tedious. So a software package like SPSS makes it easier for us. Do you remember what it looked like when we plotted one simple linear regression on a scatter plot? What happens when we plot a regression with two independent variables? Well, if you remember, when we plotted the simple linear regression on a scatter plot, we had a single line as our regression line. When you have two independent variables, we use a plane, as the picture shows here, and that's used to graphically represent the equation. If we have more than two independent variables, we're not able to use a graph to represent the relationship because graphs are limited to 3 dimensions. So let's go ahead and work an example. Salisbury Realty sells homes along the east coast of the United States. One of the questions most frequently asked by prospective buyers is, if we purchase this home, how much can we expect to pay to heat it during the winter? The research department at Salisbury has been asked to develop some guidelines regarding heating costs for single-family homes. 3 variables are thought to relate to the heating costs. 1, the mean daily outside temperature. 2, the number of inches of insulation in the attic. And 3, the age in years of the furnace. Obviously, this is a fairly simplistic example of what might be affecting the cost to heat the home in the winter, but it'll serve our purposes for building the regression model. To investigate, Salisbury's research department selected a random sample of 20 recently sold homes. It determined the cost to heat each home last January as well. And what I've done for you is provided the different values that we're going to use in our equation. The y sub I, which is our dependent variable, the x sub 1, the x sub 2, and the x sub 3, each of which are our independent variables. Let's look at the output of the regression from SPSS. We'll do the actual example in a separate video, but SPSS provides the following output for us. As with simple linear regression, the statistical analysis of a multiple regression equation is summarized in the ANOVA table. And that's our global test. It tells us whether using the regression model is significantly better at predicting values of the outcome than using the mean of the dependent variable. To review, the total variation of the dependent variable y it's divided into 2 components. We have the regression, sums of squares, which is the variation of y explained by all the independent variables, and then the error, or the residual variation, which is the unexplained variation of the dependent variable. They're both shown in the first column of the ANOVA table, and what we have here circled in red. The total number of degrees of freedom is n minus 1, right here. The number of degrees of freedom in the regression equation is equal to the number of independent variables in the multiple regression equation, and it's called k degrees of freedom. The number of degrees of freedom associated with the error term is equal to the total degrees of freedom, which is 19, minus the regression degrees of freedom. So it's 19 minus 3 equals 16. So in multiple regression, it's n minus k plus 1. The sums of squares column shows the amount of variation attributable to each source. So we have the sums of squares for the regression, sums of squares the residual, and the sums of square total. Take a moment to calculate the square root of the mean square residual right here. Calculate the square root of the mean square residual and save it for later. Now that we've done the calculation, we can build the multiple regression equation. We have the different regression coefficients. The regression coefficient for mean outside temperature, x sub 1, is negative 4.583. And the way we interpret that is for every unit increase in temperature, holding the other two independent variables constant, we expect the monthly heating cost to decrease by $4.58 per month. The coefficient is negative. As the outside air temperature increases, the cost to heat the home decreases. The attic insulation variable, x sub 2, also shows an inverse relationship. It's a negative coefficient. The more insulation in the attic, the less the cost to heat the home. For each additional inch of insulation, holding the other two independent variables constant, we expect the cost to heat the home to decline by $14.83 per month. The age of the furnace variable shows a direct relationship. With an older furnace, the cost to heat the home increases. For each additional year older the furnace is, the cost is expected to increase by $6.10 per month to heat the home. Once you have the regression equation, you're ready to go to work. In other words, calculating the regression equation is only part of the process. After we have the equation, we can use it to estimate the monthly heating costs for a home. And what do we do with these values? Well, we put those values into the regression equation. And I've listed the different variables above the quantities for the equation. So how much can we expect to pay to heat the house during the winter? Let's look at the applying the model for estimation section. What is the estimated heating cost for a home if the mean outside temperature is 30 degrees, there are 5 inches of insulation in the attic, and the furnace is 10 years old? We insert the values in place of the x variables for each of the independent variables, do the math, and create our calculation. So based on this calculation, we expect that the estimated heating cost for a home, if the mean outside air temperature is 30 degrees, there are 5 inches of insulation in the attic, and the furnace is 10 years old, we expect the cost to heat the home to be $276.56 per month. So let's see what the output looks like in Excel. Notice that we have our beta sub 0, which is our slope intercept, and then we have each of our different variables listed here, our beta sub 1, beta sub 2, and beta sub 3. And down here I've provided the steps it takes to calculate the regression for you in Excel and in Megastat. And this is provided mainly as a reference page, so you can look at it later and use it for calculating when you don't have SPSS. And here's a reference page for you that provides a breakdown of the different portions of the ANOVA table and the equations that are involved with the ANOVA table. This is the same information that I mentioned a couple of slides earlier, but now I've printed it out so you have it for reference. And we finally have another reference page with a screenshot of what SPSS linear regression, the linear regression dialog box looks like, and the instructions for making yours look like it. So in SPSS we go to Analyze, Regression, Linear, and we identify the dependent variable. We identify each of the independent variables, and then we can click OK. Once we have the ANOVA table, we can evaluate how well the regression equation fits the data. We start with the multiple standard error of the estimate. Remember a few slides back when I asked you to take the square root of the mean square residual, or the mean square error? What was the value you came up with? Well, if you did your math right, it was 5105. The square root of 2605.955 is equal to 51.05. Notice that our standard error of the estimate is the same value. How do we interpret the standard error of the estimate of 51.05 that we get from the model summary section of SPSS output? Well, it is the typical error when we use the equation to predict the cost. First of all, the units are the same as the dependent variable. In our case, our example, it's dollars. Second, we expect the residuals to be normally distributed, so about 68% of the residuals will be within plus and minus $51.05, about 95% within plus and minus 2 times 5105. Reminder, it's also the square root of the mean square residual value in your ANOVA table. Remember that the multiple standard error of the estimate is comparable to the standard deviation. As with other measures of dispersion, a smaller multiple standard error indicates a better or more effective predictive equation. When you do this in Excel, it gives you the multiple standard error of the estimate as standard error. And we can see that in the previous slide right here. Now let's take a look at our table of coefficients. from our SPSS output. The unstandardized beta coefficients in the second column. The first column is just a listing of our variables. The unstandardized beta coefficients are the values for the regression equation for predicting the dependent variable from the independent variable. The column of estimates provides the value for beta sub 0, our y-intercept, beta sub 1, beta sub 2, and b sub 3, beta sub 3. And we can see those values right in our equation below our output right here. The standardized beta coefficients, the beta uses a standard unit that is the same for all variables in the equation. It's expressed in standard deviations. In other words, it tells us the same thing as unstandardized beta values, but it's expressed as standard deviations. In our example, this would be a unit of measurement that would be common to temperature, insolation, and age. And that way, when we have the standardized coefficients, we're able to compare which variable is which coefficient is providing a greatest impact on our outcome variable. And an interpretation example that we could use in our example is that as temperature increases by 1 standard deviation, heating costs decrease by 0.754 of a standard deviation. Beta weights are useful because they can then you can compare two variables that are measured in different units, as are temperature, insolation, and age. You can get standardized coefficients with Megastat also. If you remember, when we were using simple linear regression, we had a coefficient of determination. When we're dealing with multiple linear regression, we have a coefficient of multiple determination. It's also called R squared. And the coefficient of multiple determination is the percent of variation in the dependent variable y sub I explained by the set of independent variables, and that could be however many variables we have in our model. R squared is the proportion of variance in the dependent variable heating cost, which can be explained by the independent variables temperature, insolation, and age. It's an overall measure of the strength of association. It does not reflect the extent to which any particular independent variable is associated with the dependent variable. And R is the square root of R squared, and that refers to the correlation between the observed and predicted values of the dependent variable. The adjusted R squared is an adjustment of the R squared value that penalizes the addition of extraneous predictors to the model. The adjusted R squared value tells us how much variance in Y would be accounted for if the model had been derived from the population from which the sample was taken. So the adjusted value indicates the loss of some predictive power, which is also called shrinkage. And as we just discussed, the standard error of the estimate, it's also referred to as the root mean squared error, and it's the standard deviation of the error term and the square root of the mean square for the residuals in the ANOVA table. So we did all this work to get to here. Is our model good for anything? Well, let's take a look at the global test. And the global test is what we do to test the overall significance of the model. It's just like our other hypothesis tests that we've done. We start out by assuming that nothing is going on, that all of our coefficients are equal to 0. And the global test tests to see if at least one of the independent variables, one of the predictor variables, have significant coefficients. And the way that we do that is we use the f-test. The f-test looks at whether the variance explained by the model, the sums of square regression, is significantly greater than the error within the model, sums of square residual. It tells us whether using the regression model is significantly better at predicting values of the outcome than using the mean. In other words, the global test tests whether it's possible that all the population independent variables have zero regression coefficients. In other words, they're all flat lines. If that's the case, we would be better off just using the mean of the dependent variable as our predictor. We're testing whether the independent variables in our example, which are temperature, insulation, and age of furnace, effectively estimate home heating costs. Just like all of our other hypothesis tests that we've done, we set up an alternate hypothesis, which is what do we expect to get if something is going on? And that's that not all of the beta coefficients are equal to 0. And we establish our significance level as how much risk are we willing to accept, and we'll assume that we're going to use 5.05. And then we establish our decision rule. In this case, we're using an F distribution, but other than that, it's the same, works the same way. Only with an F distribution, it's always a directional distribution. So in this case, our decision rule is we're going to reject the null hypothesis if the F test statistic is greater than our F critical value, or if the P is lower than the F critical value. So in our example here, we found an F critical value of 3.24, which is in the back of our book. The F statistic that we calculated was 21.901, and in the example that we've provided, SPSS gave us that result in the F column. Since we're using the p-value approach here, our F-stat is 21.901, our F critical value is 3.24, our p-value is lower than the F critical value. Our p-value is 0.000, and remember that the p-value is the probability of observing an F value as large or larger than the F test statistic, assuming the null hypothesis is true. So in this case, in this example, our global test is significant. At least one of the regression coefficients is not equal to 0. So this is great news, except that the global test doesn't tell us which coefficient or which coefficients are significant. It only tells us that at least one is. So the logical next question is, which one or which ones are significant? Okay, so far we've determined that our overall model is significant. At least one of our coefficients is significant. Woohoo! Now we'll determine which coefficient or which coefficients are significant. In other words, which coefficients are adding to the predictive value of the model. This test is used to determine which independent variables have non-zero regression coefficients. The variables that have zero regression coefficients are usually dropped from the analysis, and then we rerun the whole regression with all of the remaining independent variables. The test statistic is the t-distribution with n minus k plus 1 degrees of freedom. K is equal to the number of independent variables, and in our example that number is 3. So again, we go back to our hypotheses and say that the null hypothesis is when we assume that nothing is going on, and that each beta coefficient sub 1, 2, and 3 are equal to 0. And then our alternate hypothesis is when we list what do we expect to get if something is going on, is that not all of them are equal to 0. So let's go ahead and determine our t-critical values. So for each separate variable, we have our null and alternate hypotheses listed here. Same as before, we determine how much risk of rejecting a null hypothesis when it's true, in other words a type 1 error, are we willing to accept. And we're using the alpha significance level of 0.05. We develop our decision criteria for each separate variable, and it's going to be the same for each separate variable, and that is t critical value is 2.120. So we're going to reject we're going to reject the null hypothesis if our t test statistic is greater than our t critical value of 2.120 or less than negative 2.120. And we can find the critical value for the two-tailed test with 16 degrees of freedom in the back of our book in the appendix. Where did the 16 degrees of freedom come from? Well, the critical value is a t distribution with n minus k plus 1 degrees of freedom, which when you substitute through the minus 1, it comes out to n minus k minus 1. And n is the number of sample observations. We have 20 ohms. K is the number of independent variables, of which we have 3. And so our degrees of freedom is equal to 20 minus 3 plus 1, or 20 minus 4, which is 16 degrees of freedom. Now, the nice thing is that SPSS provides us with the computed t-test values for us. Again, we have all of the 3 coefficients up on the top of the screen and their null and alternate hypotheses. And what I've done is I've gone through and calculated out one t-test example using temperature. I didn't put all 3 of them up there. It takes up a little bit too much room, and you don't need to do that because SPSS provides you the solution, or the t value for you, the t-test value for you. So our t-test value for temperature is negative 5.934, which we find also in our coefficients table. And our t-test statistic for attic insulation is negative 3.119, and our t-test value for age of furnace is 1.521. Let's see where our coefficients fit related to the rejection regions that we determined from our F critical values here. So let's take a look. Take a look at this for just a second. So what does this mean? Well, I'll give you a hint. The colors mean something. So we reject the assumption that the temperature coefficient is equal to 0 because it's in the rejection region. We reject the assumption that the insulation coefficient is equal to 0, because that also is in the rejection region. However, we do not reject the assumption that the age of the furnace coefficient is equal to 0. Alright, so what does all that mean? It means that the temp and insulation coefficients add predicted value to the model, but the age of the furnace is not a significant predictor of heating cost in our model. We can drop it from the model. So that's what we're going to do. And we're going to run the regression model again without the age of furnace in it. So here we have our output based on our new regression model that does not include the age of the furnace variable or coefficient that we removed because it was not significant. We did not reject it. So here we have the output. Here are the steps to calculate the output. So we have an R value of 0.881, and that's the square root of R squared, and it's also the correlation between the observed and predicted values of the dependent variable. Now our R squared value is 0.776, and that is the proportion of variance in the dependent variable, which can be explained by all of the independent variables. So 77.6% of the variance in heating cost can be explained by the independent variables, temperature and insulation. Our adjusted R squared of 0.749 Remember, that's an adjustment to the R-squared value that penalizes the addition of the extraneous predictors in our model, and it also includes the shrinkage. It's a reference to shrinkage. And you may remember that the standard error of the estimate is the standard deviation of the error term. And if you remember from the previous slide, well, not the previous slide, but a previous slide, it's the square root of the mean square for the residuals from the ANOVA table. So take a look at the ANOVA table for just a second. Is our overall model, or sometimes called a global model, significant? Yes, it is. We can notice that because our p-value is low and lower than our significance level of 0.05. And so what does that mean? It means that the regression coefficient for either temperature or attic insulation or both are significant predictors of heating costs. Now let's take a look at the coefficients table. If you remember, the first column gives us our different coefficient names. We have our unstandardized beta coefficients, and those are the values for the regression equation, and we use those values for predicting the dependent variable from the independent variable or independent variables. In this example, the column of estimates provides the values for beta sub 0, beta sub 1, and beta sub 2 for this equation. And we can interpret the mean outside air temperature unstandardized coefficient as, for each 1 degree temperature increase holding insulation constant, the heating cost decreases by $5.15. The standardized beta coefficients, we talked about that before, uses a standard unit that's the same for all the variables in the equation. In other words, it tells us the same thing as the unstandardized beta values, but it is expressed as standard deviations. That way we can compare the impact of the coefficients against each other. In this new model, this would be a unit of measurement that would be common to both temperature and insulation. Remember, we took the age coefficient out of our equation. So what's an interpretation that we could make of the standardized coefficients? Well, as temperature increases by 1 standard deviation, heating cost decreases by 0.847 of a standard deviation, which we get from our standardized coefficients column. So I've been talking about all of these different values and what do they mean and how do we apply them and where do they come from in some cases. Well, I've provided you a reference page here so you have the definitions and what they mean and the examples that we have for those as well. If you want to copy these down, go ahead and pause your video for a moment, but I'm going to continue on. So what does our new regression model equation look like? Let's take a look. The new regression equation is y sub I equals 490.29 minus 5.1499 times x sub 1 minus 14.718 times x sub 2. We've looked at the output, all of the output, a couple of slides ago. Now we're going to go through it step by step to reinforce the concepts. So the details of the global test are as follows. Just like every hypothesis test, we assume that nothing is going on, and that's our null hypothesis. And then we have an alternate hypothesis, which is what do we expect to get if something is going on. And so our null hypothesis is that beta sub 1 is equal to beta sub 2, which is equal to 0. And then our alternate is that not all of the beta sub i's are equal to 0. And the purpose of the global test is, just like we've done in our models in the past, we have to test for the significance of the overall model to make sure that that is significant and that it adds predictive value over using just the mean of the dependent variable. We choose our alpha significance level of 0.05, and then we calculate out our F critical value, which we determine from the back of the book or from a software application. We calculate out our F test statistic, which we can do here, or we can just use what SPSS provides for us in the ANOVA table. In this case, it's 29.424, the same as we got if we manually calculated out the values. So how did our test turn out? Well, it's pretty clear since it's already showing here, but let's go ahead and take a look at the next slide. Here we have our F distribution with our rejection region highlighted or shaded. We have our F critical value of 3.59 and our computed F of 29.424. So, do we reject? Well, it's in green. It's pointing to the rejection region. The value is 29.424, which is above our F critical value of 3.59. So yes, we reject the null hypothesis. So our overall model is adding predictive variable. At least one of the two beta coefficients is adding predictive value to our model. Now that we know that our overall model is significant, which means at least one of the coefficients adds predictive value to the model, what do? We test the individual coefficients. And just as before, our upper and lower t critical values are negative 2.110 and positive 2.110. We have our two coefficients here, and we calculate out the alpha, or we choose the alpha of 0.05. We have our t critical value. We have our t critical on our distribution chart, and then we get to determine the t-test values for each of the coefficients, and we plot them on our distribution, and we find that temperature is negative 7.34 and insulation is negative 2.98, both of which are less than our lower t-critical value. Do you remember what it means when we have each of our test statistic values in the rejection region? It means that we reject the assumption that the temperature coefficient is equal to 0, and we reject the assumption that the insulation coefficient is equal to 0. Okay, well, what does that mean then? What that means is that temperature and insulation coefficients each add predictive value to the model. So finally, success at last. Now we can go home. Well, not really. How do we report what we found? Here are some guidelines for reporting your regression results. Frequently they were presented in a table along with the write-up, and as a general rule of thumb, any table that you add to your paper should just complement the text, and you should not replace your text with the table. And another rule of thumb is to present your data in just a results paragraph without the table if you have 3 or fewer sets of numbers. Your results go in the results or the findings section of your text, and you want to make sure that you list the F-test for the global test and the T-tests and standardized regression coefficients for the regression model. And this example here, you want to also provide all the corresponding significance levels for all your statistical tests, and this is a APA format right up here where you have your F test with 2 degrees of freedom in the numerator, 17 degrees in the denominator, and you get a 29.424 as your F statistic, and the p-value is less than 0.001. And you want to talk about how it explained the variance of the model and the effect size, which you'll see in the example write-up. And you also want to ensure that you report any insignificant values that you may have come up with. So let's take a look at the table. And this is an example of a regression table that should be fairly close to accurate APA formatting for it. And it's Table 2, Simultaneous Multiple Regression Analysis. This is where you'd put your outcome of your multiple regression analysis. At the top we have the title, we have our n equals 20, we have our listing of our variables, mean outside air temperature, attic insulation in inches, and then our slope, or excuse me, our y-intercept, our constant. Then we have our unstandardized beta coefficient under the B. Then we have the standardized error of the unstandardized beta coefficient. And then we have our standardized beta coefficients listed here. We have an asterisk here to show that we have statistical significance at the p is less than 0.01 value. You may be wondering why it says only p is less than 0.01 instead of 0.001. Well, if we go back to our slide 20, you'll notice that the significance level for the attic insulation was 0.008 and not 0.000. So we want to make sure that we are comprehensive and we cover both of the variables, or both of the coefficients. So both of them are the p is less than 0.001. Although the mean outside air temperature, the p is less than 0.001. And we could separate that out, distinguish that separately by one asterisk and then two asterisks, and have separate indications there. And that's probably a better way to do it. But seeing as this is a pasted image from a Word document, I'm not going to go ahead and make the change now because I can't make it in the PowerPoint. And notice in red I have a note here that this table violates the rule of thumb on the previous slide, but it's provided as reference, and that particular rule of thumb is that just use a results paragraph if you have 3 or fewer sets of numbers. But again, this is just an example. You would have several more if you were doing a larger multiple regression analysis. Okay, so we have this really pretty table. How do we actually write it up? And this is an example write-up based in the APA format for your multiple regression analysis. You'll note that the first reference that I list on the page is actually part of the write-up, but the second one is the source for this write-up. It's predominantly what I used as a template to write up this paragraph. I strongly encourage you to check out SPSS for intermediate statistics use and interpretation if you're looking for a quick reference for how to run SPSS, how to interpret the output, and how to write it up. That's all for this video.